All right, we didn't really have time the last time to talk about this last bit of 3.2. It's one of these things that when you're looking back on it later, I think people sort of say, well, what do I do with this? Like, this is an idea. It's not really something you do something with, just, understanding a concept. It's not like, okay, now we're going to learn how to solve equations, or now we're going to learn how to find the derivative of something. This is just connecting those two things, differentiability and continuity. If something is differentiable, it implies that it's continuous. This is a one-way relationship between those two things. Remember that for something to be differentiable, if I draw something like that, it's not differentiable at whatever this x value is here. It's not differentiable because on one side the slope looks like it's positive something, and on the other side it looks like it's negative something. It's not differentiable there. If you draw something that's differentiable, you can't do it without it being continuous. Differentiable means it's a nice smooth change at every point in the slope. There's no sudden slope changes. There's no way to draw it so that it's differentiable but then turns out to be not continuous. So this implies this one way, right? If it's differentiable, then it's continuous. You have a lot of statements in math that are two ways that you could turn them around, right? But this one is one that goes only one direction, right? If this is true, then this is true, but it doesn't go the other way. If it's continuous, that doesn't necessarily mean that it's differentiable. That's what this second statement here says, to do it the other way, right? This is differentiable everywhere. And you notice that there's no way to draw a curve like that without making it continuous. But if you do the opposite, you can draw something that's continuous, but make it so it's not differentiable, right? Here's something that's continuous, but it's not differentiable. That's kind of all this is about here, okay? You can try and do all the different cases here, all the different, differentiable means it's continuous. This is continuous, not differentiable. Okay, not necessarily differentiable, right? So the relationship doesn't work that way, right? If you think of this relationship as if A then B, that works, but it doesn't work if B then A. Okay, it doesn't work this way doesn't work if you turn it around. Are we okay with that idea? You can try and draw a few different graphs right now, maybe to illustrate that for yourself. Draw a couple that are differentiable everywhere. I mean, pretty much any smooth curve, right? It's not differentiable if you put a jump in the thing. It's not differentiable if you have an infinite kind of discontinuity. If you make it so that it's differentiable, the only way you can do that is that it's continuous. Okay? As long as you have a graph kind of showing each of those things, then I think you're good. Yep. If there's any kind of discontinuity, like the contrapositive of this statement, this one says, it's actually too bad that in Math 11 you don't do this logic unit. You learn to look at statements. I think I've said this before, but like if A is true, then B is true. There's something called the converse of that is if B is true, then A is true. That's called this is the converse of this statement. That's not true in this case. But there's also something called the contrapositive. If not B, then not A. Is that true? So what would that be in this case? That would be what I think you're saying, right? If it's not, whatever the second thing is, right? If it's not continuous, then it is not differentiable. Is that true? Is there any way if it's not continuous, so draw a bunch of different things that are not continuous, right? Like the one I just did there. That's definitely not differentiable there. Like this. or even just a vertical tangent. These are wonderful graphs here, but it's not differentiable there. Sorry, I got to make it not continuous. I'm doing it backwards. If it's not continuous at that point, what other kinds of things could we have? We could have this. What are the derivatives of either side of that? What's the left-hand derivative of this thing? The derivative if you approach from the left side here. This could be tricky here. This might work. Never been attempted before. Well, maybe. If the derivative as I approach from that side, what's the derivative? Infinity, right? What if I go? Won't let me go to the other side. But if I go to the other side, what's the derivative as you approach from the other side? What's the derivative as you approach from this side? Negative infinity, right? That's not differentiable there, right? Because of this point up here. If you make it so that it's not continuous, it can't be differentiable. It's the contrapositive of this statement. That's true. It doesn't, like the converse doesn't work. If it's continuous, it doesn't necessarily mean it's not differentiable. But if you turn it around and put not in front of it, then it's true. Okay? Again, it's not really anything to do with that. It's just to try and make the connection for yourself between continuity and differentiability. One doesn't always imply the other. It's a kind of a one-way relationship. Are we okay with that? Maybe, yes, no, yes? Well, then the function's not even defined there, I guess, right? So is it differentiable at that point? To be differentiable, you have to have a point there, right? Because when you're doing the definition of the derivative, you're doing the function value above that, like away from that point, but you're also doing the function value at that point. So if there's no point there, then it's not going to be, the derivative's not going to exist there. Yes?
The function can be continuous even if it has a point of discontinuity.
Yes.
Does that apply for
this?
As well? That can be a differentiable function even if there's a point where it's not differentiable.
We're talking about at a point, not whether a function's continuous or not. We're talking about at a particular point, and even though, like, a function that goes like this, even though this has a discontinuity at 0, it's called a continuous function because it's not defined there in that whole thing, not to dredge that up again, but we're talking about at a point. Like, there is a discontinuity at 0. That's what we're talking about here. So this is talking about differentiability at a point, because you can only talk about differentiability at a point. I mean, you can say a function's differentiable everywhere, but it's looking at each point individually. And for the purpose of this, we're talking about continuity at any given point. Okay? Think about it sometime. Have a look at some of the questions that are on the assignment that you do, and I think it'll be fine. Okay? We're going to look at this is what 3.3 is what people remember from first year calculus. So you'll like this. Well, you won't like it, but